So hello everybody, welcome to the first season of the Beyond Diagonal Reconfigurable Intelligent Surfaces webinar series hosted by IEEE Communications Society, Radio Communications Committee, a special interest group on Beyond Diagonal RIS, which is chaired by Professor Bruno Clerks. So my name is Arman Shojai-Fard. I'm a senior manager of engineering with Interdigital based in London, UK, and I'll be your host for today's session. So this webinar series aims to provide a forum and bring together researchers, industry practitioners, and individuals for the dissemination of the latest research, innovations, and applications of Beyond Diagonal RIS. And in this series, we have 8 leading experts from academia and industry that will share their ideas and work on Beyond Diagonal RIS and latest findings and state-of-the-art results. So it is with a great pleasure to have the first webinar of this series given by Professor Marco Di Renzo. So before I introduce our speaker, some housekeeping rules for the session today. So the duration of the talk is 50 minutes. And audiences will be muted during the talk. But you are welcome to post your questions in the chat. And then we would have a 10-minute Q&A towards the end, where we will unmute 2 to 5 audiences to raise questions, and we'll also take questions from the chat. So with that, I will now introduce our speaker, which requires no introductions whatsoever, but I will give it a go. So Professor Marco Di Renzo is a CNRS research director and the head of Intelligent Physical Communications Group in the Laboratory of Signals and Systems at CNRS and Central Supélec, Paris, France. He's an elected member of the L2S Board Council and a member of the L2S Management Committee. Marco is also a founding member and vice chair of the IEEE Industry Specification Group on Reconfigurable Intelligent Surfaces, where he also served as a rapporteur of the work item on communication models, channel models, and evaluation methodologies. He's a fellow of the IEEE, IET, and AIA, and he is a highly cited researcher. He holds the 2023 France Nokia Chair of Excellence in ICT, a fellow at City University of New York, a Nokia Foundation visiting professor, and a Royal Academy of Engineering distinguished visiting fellow. He has won many awards, including 6 just in 2023. So I will not go through won't be able to go through the list today. He served as the editor-in-chief of IEEE Communication Letters and is now on the advisory board. And in 2024 to 2025, he will be serving as a voting member of the Fellow Evaluation Standing Committee and the director of the journals of the IEEE Communications Society. So with that, I will give the floor to our distinguished speaker. Marco, the floor is yours.
Okay, so thank you very much, Arman, and for the kind introduction, and thank you very much, Bruno and Matteo, for putting together this, very nice and timely, group of SIG, which is very much of interest for the community working on on RIS. So it's a great pleasure to see all of you, and for me it's the first presentation of the year, so I take the opportunity to wish you all the best, and and I hope that you had a great start. So then I will try now to share my screen, and yeah. All right. Okay, so hopefully you can see it right now.
Yeah, I can see it, Professor.
Okay, great. Okay, so as I said, so today I will be talking a little bit about this RIS and beyond, basically only the diagonal RIS, but also the beyond RIS, which is the main focus of this group, and towards basically the end. The main idea is to give you an approach, a model to study and to analyze and to optimize RIS, which departs from electromagnetics, and this approach is pretty, promising, especially if you want to study beyond RIS for reasons that I will tell you towards the end of this presentation. And also I take the opportunity to acknowledge some of the funding agencies here that are supporting, besides the IEEE. These research activities, there are European projects and national projects as well. So, as I said, it will be an approach based on multi-port network theory for modeling these kind of structures, and the role that is going to play for beyond diagonal RIS. And I'd also take the opportunity to say this is I will present some of the research works in collaboration with Bruno, with Matteo, and their team at Imperial College London. So I guess that we know now what this meta-surface-headed wireless is, this RIS and holographic surfaces. So I'm going to go just a very brief intro here. I'm not going to spend much time, and I will dedicate all the time to the really the multi-port network theory and what it can bring to this field. So first of all, in this very quick introduction, let me tell you that if you are interested in knowing what these RIS or smart surfaces in general are, especially if you are interested in understanding what is happening at the intersection of communications, signal processing, and metamaterials and antennas, this is one special issue that was published more than 1 year ago, but it's tutorial-based papers, so is always of interest if you are trying to start your work on this field. So essentially, these smart surfaces, and then we will see that this conceptual representation can be applied in many cases, are fundamentally surfaces. So we have a substrate, and then on top of it, we have some tiny antenna elements. So these radiating elements in red, which are called unit cells or meta-atoms. So only the red elements are passive, so that there are no active elements there, and they are able to shape the waves that illuminate this structure. So depending on their physical size and geometry shape. If you want to make this surface reconfigurable, so if you want to change the way that this structure modifies the waves, we need to add some electronic circuits, which are here represented with these tunable elements, which can be diodes, varactors, and this basically allows us to change the response of this structure. Okay, so the surface is not per se completely passive, it's nearly passive, because we need some power for this electronics, but we don't have power amplifiers and RF chains. That's the idea. So you can do two main things with these surfaces. At least these are the two most common applications. You can use them as a smart reflectors, for example. So here, in principle, if you illuminate this surface with this signal here, you're going to get this specular reflection, which is either wasted throughout the environment, or it may even generate interference towards other receivers. Through these devices, you could change basically the direction of radiation. So you could bend basically these electromagnetic waves as your desire, which means how you configure your electronic circuits. And this allows you to enable communications in those areas that are where there is no coverage, for example. Another application is to use them to simplify the design of transmitters, MIMO transmitters. So one idea, in general, basically, if we have a MIMO transmitter, we have a significant portion of the processing and the complexity and the energy consumption is associated to this baseband digital processing. Then we also have some high resolution digital to analog converters, RF chains. We may have everything done digitally, or we may have an hybrid architecture with phase shifters as well, as it is shown here. One idea would be to move from a digital implementation of beamforming, pre-coding, onto a wave domain processing of the signals, because this allows us to reduce the complexity, to reduce the energy consumption, etc. One idea is the one that is shown here at the bottom, where, as you can see, you remove the digital baseband processing. You may have also low resolution digital to analog converters, and then always a few RF chains if you want to send more streams. Okay, not only one stream. But then essentially the idea is that you can include into your transmitter these reconfigurable surfaces. Here, this is an example where you have multiple reconfigurable surfaces stacked one after the other. The distance between them is very tiny, a fraction of the wavelength, and therefore you are actually implementing something that looks like a deep neural network. Think of this surface, each of this layer, as a layer of a neural network, and each of those meta atoms, unit cells that I told you before, like a neuron in your DNA. And the signal goes through the structure directly in the electromagnetic domain, and then you transmit it. This allows you to implement beamforming. Then today I'm not going to go much into these details, but the same approach, actually, even it's more state of the art related in terms of modeling. Multi-port network theory can be applied for this structure as well, but for simplicity, I will focus on RIS today. Okay. So what we need to understand is that from the technology point of view, the RIS or this SIM or holographic MIMO, they are based on the same metamaterial technology, so they need reconfigurable metasurfaces or dynamic metasurfaces, as they are called. But on the one hand, the RIS, usually we don't want power amplifiers, no DSP, no RF chains. In this other case, if this metamaterial is part of the transmitter, then we always have some power amplifiers, RF chains, etc. So the technology is the same, but the requirements are slightly different. The modeling can be done in a similar manner by using multi-port network theory. So now, what is going to happen if you take these devices, whatever you want to consider, holographic surfaces at the transmitter, RIS, and you deploy them in a wireless environment? So you may get something like this. So what really characterizes an environment of this kind is that these surfaces usually, in order to provide some gain, especially RIS, because they are passive, so they don't amplify the signal, they need to be sufficiently large in size, so electrically large. And also, if you don't want to make them too large, they should be sufficiently densely deployed in order to have them close to you. This implies that in most of the cases, we need to distinguish between two propagating conditions. One is the far field and one is the near field propagation. Okay, so that's one of the main things. So if you have these very large surfaces, what is going to happen is that either the size is getting very large, which means that many users which conventionally were basically in the far field now are in the near field, because this boundary that distinguishes, if you want, the near field from the far field moves towards the right. So more users. So basically, you're expanding this near field region. That's one of the things, which implies that we need accurate models that allows us to account for the near field. And the other point is that, as we will see, this is especially relevant for beyond diagonal RIS. We may want to have surfaces where there are many ways, to justify this. Now, I will give you two possible justifications. One is that in typical antenna array designs, we have these kind of structures. So we have elements that are located that are spaced lambda over 2. This creates a surface that is relatively sparse. So in some sense, we are not utilizing the entire surface to our best. So one idea would be to densify the number of elements on this surface in order to have an effective aperture, which coincides with the geometric size. And this allows us to put more elements on the same surface, and therefore to possibly have a better beamforming gain. But if we do that, we cannot ignore the mutual coupling between the elements. That's one point. Another reason is that, as I said, these surfaces needs to be quite large. And then if you start putting your elements lambda over 2, then the size might be huge. If you want to reduce the physical size, you may want to have a given number of elements within a smaller space, and which gives you which means that you cannot in any case ignore this mutual coupling, electromagnetic mutual coupling anymore. These are two practical justifications. Another justification might be that some owners of some antenna space, they may tell you, okay, I own that space, that number of square meters. How can I best utilize that space if I can put so many antenna elements? There is also quickly another justification, which is more fundamental, more theoretical. There are a few papers that discuss that, but I like this paper here from Hansen because it's a mathematical based paper. So even though it's written by a person with a lot of experience in electromagnetics. So what this paper says the following: imagine that you have your RIS, your metasurface, and you want to illuminate basically this surface, and you want to optimize the structure in a way that you take a signal from a given direction and you bend the signal towards another direction, which is the basic operation that an RIS needs to do. Okay, and now in this paper, the author models this metasurface as an infinite number of wires. Okay, the wires are going out of this slide, and when you see these red dots, there is one of those wires. The reason why wires are utilized is because they are mathematically tractable with respect to more realistic structures. And then he says, here, the idea is to optimize the location of these wires in a way to be able to have one single plane waves that illuminates the structure, and you want to irradiate only one single plane waves without spurious reflections or without significant side lobes, where it proves mathematically that you can mathematically have only one single plane wave, provided that the current distribution on this device is continuous. Okay, so which means that with a discrete number of wires, you cannot achieve these results. Okay, at least mathematically, from a mathematical point of view. So this essentially justifies that this densification of the elements, if you want to have a very clean irradiation pattern, and if you want to really have a very high efficiency of irradiation towards the direction of interest. Okay, that's the reason why this mutual coupling, from a mathematical point of view, can be of interest to be studied. And multi-port network theory is, to the best of my understanding, a good tool to model this mutual coupling. So what is this multi-port network theory? First of all, it's not a new thing. It has been there. It's available in books. We know that. One paper that is very popular, I do recommend you to read it because it's very nice, is this one from Professor Nosek, who was written quite a few years ago in 2010. And where basically there is this proposal of building a circuit-based model for a communication link. Of course, it's not only a communication link, it can be an entire communication network. And basically what I will tell you is based on this paper and applied to RIS, departing also from some material that is available in books. So I will go through a step-by-step approach so as to give you the idea of what it's happening. And also, the main aim of this presentation is to show you how multi-port network theory, even though for some super expert in metamaterials might be considered to be relatively simple, considering the techniques that the other people utilize, but it's sufficiently good, in my opinion, for us and allows also to understand the fundamental limitations of the models that we are utilizing now in wireless communication. So it can be a nice bridge between communication theory and antenna theory, in my opinion, and I will give you more details in a while. So, but in any case, if you want to get the background, I recommend you to read this paper. So let's start from a simple case study, the basic scenario where we have an RIS in free space. Let's see how we can apply this technique, this approach, and what we get. So free space means fundamentally that we have one base station which could have multiple antennas, and then we have multiple users, or one single user with multiple antennas. It doesn't really matter. And then we have one RIS with many elements. The point is that there are no other objects, I mean, in the environment. So free space means that there is only the RIS in the environment that we consider. So if you want to have the details of the derivation, I will suggest you to read this paper. I will just give you the main results and the finding, because the most important part that I will present you today comes in a while. So fundamentally, the approach is the following. We have a transmitter which is modeled as a set of antennas. Now here we utilize dipoles for modeling these antennas. There are a few reasons for that, which I will tell you in a while. But I mean, we have a dipole which is connected to a voltage generator. The receiver, at the receiver, we have dipoles connected to a load impedance, and the RIS, we have again dipoles connected to tunable impedances. So here the impedances can be tuned, and they are the optimization variables. So the dipole has a fixed size. We don't change it. The reconfigurability comes from the impedances connected to the dipoles, and these dipoles can be arbitrarily close to one another. Therefore, we do not ignore the mutual coupling. So the idea is that we want to write an end-to-end channel model which links the voltages that we measure at the receiver as a function of the voltages that at the generator, or the voltages here at the port of the transmitter. It depends how you want to see the things. But the idea is to get a formula of this kind. Where in this channel end-to-end, we want to include everything, which means the characteristics of the dipoles, the path loss between the transmitter and the RIS, the scattering from the RIS, the mutual coupling between the RIS elements, and so on and so forth. So the reason why this is a good approach, I mean, multi-port network theory allows us to do that. The reason why this is nice is because this looks like a MIMO equation. Okay, so, and we are familiar with MIMO equations. So this may be an enabler then for doing optimization, as I will show you. So long story short, why do we use dipoles? There are two reasons. One is that for analytical tractability is one of the few antenna devices for which we can do some math in a relatively simple manner, even modeling the field in the near field. This is available in books under some approximations. But also because there are results in the metamaterial community that shows that complex materials could be approximated with a discrete set of dipoles with some characteristics. And the characteristics of the dipoles, length, radius, the impedance connected to the dipole, depends on the material characteristics, which are called the polarizabilities of the material in jargon. So this can be applied to active antenna elements and to passive antenna elements like RIS. So that's the reason why the two reasons why we utilize this approach. We use dipoles. Okay. So now, if you're not familiar with the mutual coupling, just one slide to recap it. But the main idea is that if you have two antenna elements sufficiently close to one another, and you illuminate these two elements with a plane wave, there is a current that is generated, for example, on these antenna elements. These currents create a field that is radiated. the effect of this radiated field on the antenna itself is this self-contribution, this self-impedance. The effect of this radiated field on nearby antenna elements is the mutual coupling. And usually it is defined in this way. So this formula can be proved in different ways, but I mean, let's consider it as a definition for today. But the important point to understand is that there is it depends this strength of the interaction between the antenna elements from the electric field that is generated by one dipole and is observed on the surface of the other dipole, and that is projected on the currents that flows on the dipoles where you observe the field. Okay, this can also be derived from the method of moments, but that's the general idea. So, long story short, what is the approach that is utilized in order to develop this multi-port network theory model? We apply the superposition principle. So we have many elements in the network. So we have one transmitter for simplicity, which generates an electric field, one receiver which generates an electric field, and we have multiple RIS elements, each of them generating an electric field. So in any point of the space, the field is the sum of all these electric fields. And if you observe this field on the surface of every of the dipoles available in the network, this sum is equal to 0 because of the boundary conditions on a perfect metal. There is no tangential component of the total field, except at the ports, where at the ports you have your voltage. The voltage can be obtained from the Ohm law, depending on whether you have a voltage generator or an impedance. It doesn't matter if it's tunable impedance or not. And once you have these formulas, you project them on the currents flowing on each of the devices because of this definition of mutual impedance, and then you end up with this end-to-end channel model. That's in simple terms, I mean, what is done in this paper. Okay. So now this end-to-end channel, which connects the voltage at the receiver and the voltage at the transmitter, so it gives us the transfer function. It's a bit nasty, I mean, in this formulation, but what we really need to understand, then I will show you simplified formulas, but what I want to emphasize is that there are two key elements here. One is the impact of the mutual coupling. So this is a matrix that in general, a full matrix. Okay, there are even the off diagonal elements are not 0 because of the mutual coupling, and then there is this matrix of tuning circuits, which is basically this circuit here. Okay, so if the structure that you have is a diagonal RIS or a conventional RIS, this matrix is diagonal. If you don't have a diagonal, a conventional RIS, but you have a beyond diagonal RIS, this matrix is not diagonal. Okay. So, and this makes things quite a bit more complicated to be analyzed, but I will show you what we're gonna have. It's gonna happen, I mean, towards the end of this presentation. Okay. So that's what this approach allows us to do. The important point is that we can clearly identify in this analytical formulation the impact of the loads that are optimization variables and the impact of the mutual coupling. Okay. So now, then of course, I mean, when we submitted this paper, I mean, we got, positive comments, but also some kind of complaints, or at least, I mean, people asked, can you apply this in a multi-path environment? Because of course we are considering a wireless. So, and then we were working at this problem, and indeed you can generalize this approach also in the presence of multi-path. So how can you do that? So now this scenario is slightly more complicated. So it's the same as before, but now you add some scattering clusters. So you have this, I mean, it can be a tree, it can be a wall, whatever you want. But the idea is that each of these scattering clusters, we can model it always by utilizing multi-port network theory. You can model each of these devices as a multi-port network, which you distribute into the scenario. And therefore, you may model it as a bunch of dipoles that are connected to impedances. Okay, so even the multi-port can be viewed as a multi-port network. And the objective is always the same, to obtain this end-to-end channel model. Now, the details are in this paper, which is a joint work with some collaborators. The main idea is the following, again, is that if you have a material object, okay, there are papers that shows that again you can apply this discrete dipole approximation. So depending on the polarizabilities, the physical properties of this material, you can map these physical properties onto a representation given by a discrete set of dipoles and then in a multiport network. I mean, one of the papers that I recommend you to read in order to see this connection between the modeling of metamaterials and the loaded wire dipole approximation is this one written by one of my collaborators, Professor Tetrakov from Aalto University, which was actually written 20 years ago. Okay, so you can have a look, but this is one of the theoretical foundation behind this approach. So now, long story short, the proof is the same as before. It doesn't change much. But the point is that here we have already slightly simplified something. But the point is that without multipath, without basically, in the presence of multipath, you get a model that after some simplification looks like this. Now, what is here the main difference with respect to the model that I showed you before? Before there was this matrix, which was the mutual coupling, and then there was this other matrix, which was the electronic sequence, diagonal or not diagonal, depending on whether you have a diagonal RIS or a beyond diagonal RIS. But now we have another matrix. This matrix accounts for the interactions between the scattering elements, so the clusters, and the RIS. So as you can see, in general, when we open these wireless papers, we always see that there is the channel is written as what happens in free space. Okay, so there is one term which is free space, plus we add the multipath. Okay, the component of the multipath, and the only things that we take care is to split the power between these two components in order not to create more power in the channel. But here we can see that the end-to-end channel mode is not linear, because this multipath components is inside a nonlinear term, which is this matrix inversion. Okay, so while you can do an approximation, you can expand this at the first order, but in general, there are these multiple interactions that make the things more complex. So this is, to me, an interesting finding from that multiport network theory allows us to make, which is basically clearly adding this multipath in an electromagnetically consistent manner into the modeling, and to see that some of the models that we are utilizing may, I'm not saying that they are wrong, but they are based on some simplifying assumptions that that multiport network theory allows us to see, to explain, and to justify also what the specific assumptions are. And this I will go back to you later on. Now, in this presentation, I decided not to spend too much time on optimization, because I think that in our community, optimization is something that it's more we are more familiar with. It's never easy, but we are more familiar with. So I decided to focus more on the modeling part and the connection with electromagnetics, because it's maybe something that we are not much used to. But once you have this MIMO-like equation, of course, you can write your optimization problem and try to maximize the rate, because your channel looks like a MIMO channel. It's only the structure of the channel that changes. But this structure of the channel creates some problems, because now your optimization variables, which is this matrix of with the impedances, diagonal or not, is inside this inversion operation, which complicates the things. But I mean, if you want to have what is happening in terms of optimization by utilizing this model, you can have a look at this paper and other papers that I will show you in a while in collaboration with Bruno and Matteo. That's just something to give you a reference at this point. So now, just I want to show you one result. So now, imagine that you have this network where you have MIMO interface channel, two transmitters, two receivers that want to talk to each other, and then there is blocking objects, and so they cannot utilize line of sight communications, but you want to use this RIS. You model everything with a bunch of dipoles with multiport network theory, and you write the model and you optimize it. So the idea is to understand what is the impact of mutual coupling. So this is the sum rate of the system. There are many lines here, but you just need to look at two of them. One is the black line. So the black line is what happens when you have a surface and the only scattering elements that are on the surface which models the RIS are the blue ones. So the red ones don't exist. Okay, so you have lambda over 2 spacing. You can see that you have this line, which is the reference line. Then what you do, you take the same surface and you keep adding elements, which are the elements in red. So you make the spacing between them smaller, smaller, smaller. So let's focus only on 2 lines, which are those in purple. We have 2 lines. One is dashed lines and one is a continuous line. So the dashed lines, is this one, is the case where you densify the surface, you add the points in red, but you don't take the mutual coupling into account. You assume that the matrix that characterizes the system is diagonal. Okay, and you can see that it's a mismatched design, and you can see that you have a performance degradation, even though you have more elements. If you, on the other hand, take into account the mutual coupling, the model that comes from multi-port network theory, you can capitalize on this mutual coupling and to get good performance. So you densify, you have more elements, and you take advantage of these more elements if the mutual coupling is well modeled, and then it's taken into account in the optimization phase. Okay. So I have another 20 minutes. So now I want to tell you a few important things here. That is the most important part of this paper, but this presentation. But I wanted to give you some background if you're not working on this field. So what really multi-port network theory allows us to say that communication theory does not, or simplifies. So the reference paper is this one, which is written by a couple of collaborators from University of Siena. Yeah. One is Andrea Abrardo, who is an expert in optimization, MIMO, and Alberto Toccafondi, who is an expert in electromagnetic theory, antennas, and physics. So let me tell you, first of all, we utilize in this paper this multi-port network theory. Now, if you want to know really more on multi-port network theory and the different techniques that you can apply, I do recommend you to read this paper written by Matteo on that really overviews the different techniques that can be applied and also explains the relationships between the different approaches and when it's more convenient to use one representation or another representation. And this is also part of the presentation that I'm gonna give you today. But long story short, if you have an RIS-headed system of the one that I showed you, you can always view the entire system as a multi-port network, where some of these ports are dedicated to model the transmitter, some of these ports are dedicated to the RIS, and some of these ports are dedicated to the receiver. Now, you can model this network in different ways. Today, I will focus on 2 ways. One is by using the matrix of impedances. The matrix of impedances links the currents that are flowing through any of these ports with the voltages that are available at the ports of the ports. The reason why I like the impedance representation is that the impedances are directly connected to the physics of the signals that propagate from one point to another, as I will emphasize in a while. But there is also another representation, which is the scattering parameters, which I will show you that can be quite convenient from the point of view of the optimization. I will show you some results. What are these scattering matrices? These scattering matrices connect the waves that enter into the ports with the waves that exit from these ports. So the reflecting waves with the impinging waves. So this is more similar to the vision that we have in wireless communications, and is also directly connected to the reflection coefficient. So it's something that we like. Even though we need to be careful, and that's what I will try to tell you in the next few slides. So you can use these 2 representations. Now, if you apply multi-port network theory and you consider the RIS as an example, I'm not going to give you all the details. I've already showed you some examples of derivation, but you can have that your end-to-end channel in general can be written in this way. Now, this representation works regardless of using dipoles, not dipoles. This is implicit in multi-port network theory. Okay, it doesn't matter whether it's a dipole or not. Now, the key point here is that this matrix here where you have, again, the matrix of the mutual coupling and the matrix of the tunable elements. So this matrix can be diagonal if you have a conventional RIS, non-diagonal if you have a beyond diagonal RIS. Okay. You can do the same by using the scattering representation. With the scattering representation, you have something like this, where now the matrix SSS models the mutual coupling between the elements, and gamma S is the matrix of reflection coefficients. Okay, this matrix of reflection coefficient is defined in this way, and again, if ZSS is diagonal, this is going to be diagonal, but if ZSS is not diagonal, gamma S is not diagonal. Okay, that's a sense. So it can be applied to both structures. Okay. So now, one of the key messages that I want to convey in this presentation is that these two representations are both good, they are both correct, they give us the same end-to-end channel, but we need to be careful on providing the correct interpretation to each of these terms that appear in these equations, because this allows us to highlight the powerfulness, I would say, of multi-port network theory. So the details are available in this paper, which was written. The main author is Hongyu Lee, who is a team member in Bruno teams at Imperial, and there is Matteo and Shunpu Shen and Bruno, of course. So what we do here in this paper, and then I will go back to this paper with some results towards the end to try to explain you the impact of mutual coupling in beyond diagonal RIS. In this paper, what we do is the following. We try to connect the scattering parameters with the impedance parameters and try to see whether there are differences between them. Now, I'm not going to show you the proof, but the formulas that you get are these ones. Now, the most interesting comments are those related to this term here that I want to describe to you and tell you what the main differences are with respect to our understandings today. So let's focus on this term. So now, what is this term? This term, in principle, is the term that connects the transmitter and the receiver, which in principle does not go through the RIS. But look at this formula. The scattering parameters that links the transmitter and the receiver is given by one term, which is the impedances between transmitter and the receiver. And then there is also this other term here. So first of all, here we understand that the S parameters, SRT and ZRT, are not the same thing. Okay, so if we go back, if we go to this representation, as you can see here, and then we go to this representation, and you try to connect together terms with the same indices, they are not correct. It's not correct. It's not the way to do. Okay, it's not the way to proceed. The other point is that we see that the scattering parameters is given by the summation of two terms. One is this impedance, and one is another term which depends on the RIS. So even though we term this contribution transmitter receiver, it actually indeed depends also on the presence of the RIS. And the contribution from the RIS is when all the impedances are basically loaded to the same impedance, which is the reference impedance. This is what physically this means. Okay, so what is this term? Fundamentally, this term is related to what is called the structure, it's not exact, but it's related to what is called the structural scattering of the RIS. So the RIS, the fact that it's there, the fact that it is made of element devices, it scatters, basically, and this is what it's basically contribution. So let's see this. Here we have that this structural scattering, which is this term here. What is this? It is a specular reflection that the RIS generates. So when you illuminate the RIS generates a specular reflection just for the fact that is there. And why this is a specular reflection? Because, as I told you, this corresponds to the term scattered by the RIS when all of its impedances are the same. And this is by definition a uniform, an homogeneous surface, and therefore we have a specular reflection. What any material would do if we don't change, we don't apply a phase gradient. So we have here two conclusions. The first thing is that the scattering parameters transmitter receiver is not the same as the impedance between transmitter and the receiver, and it includes what is called the structural scattering of the RIS, which is independent of the reflection coefficient of the RIS. That's the point. Now, what we need to understand is that the ZRT is the physical transmitter to receiver link. So it's really the link that exists if there is no blocking object between transmitter and receiver, because it depends on the electric field between transmitter and receiver. Okay. On the other hand, the scattering parameters SRT is non-zero even if there is no direct link between transmitter and receiver because of this structural scattering. So let me give you an illustration. Imagine that you have this setup. Then, if you have the direct link, both these two terms will be not equal to 0. Imagine now that there is an object between transmitter and receiver, then the ZRT is equal to 0. But in the presence of an RIS, SRT is not equal to 0 because there is the structural scattering. Okay, that's essentially the main point. Okay, and this is typically ignored in communication theory, the models that we utilize. So now, what are then the implications of all that? The implication is, in simple terms, I will give you just an illustration which comes from the mathematics that I showed you, is the following. Oops. Yeah, imagine that you have this link, these three links, okay, from transmitter to receiver, and then this scattered field from the RIS. Now, consider now this representation in terms of scattering parameters, and compare it with the representation that we typically utilize in communication theory. I used a different notation in order not to misunderstand that H with S. They should be the same, but we will see that they're not exactly the same. So we see the following. The direct link, typically in communication theory, we associate this direct link HRT with SRT. But HRT, when we write in communication theory, has nothing to do with SRT. Indeed, this HRT is what comes from ZRT, because it's the physical link between the transmitter and the receiver. Because in SRT, there is also the structural scattering. So if this is blocked, there is something more. Okay. In addition, if we look at the impact of the scattering from the RIS, usually we model the RIS only through this reflection coefficient, but multi-port network theory tells us that the structure of the scattering is much more complex. We have this reflection coefficient, but we also have this impact here of the mutual coupling. The important point is that these two models match with one another only if this matrix SSS is equal to 0, which is not only if we ignore the mutual coupling, but is much more than that. Okay, so there is a fundamental difference between these two models. Also, if this reflection coefficient has an amplitude equal to 1, which is what we usually assume in wireless communications, this structure, this term here that comes from multi-port network theory doesn't have an absolute value equal to 1. And even if you can make this reflection coefficient, the amplitude and the phase independent of one another, these terms will not give a phase and an amplitude that are independent of one another. So the models, this multi-port network theory allows us to highlight clearly all the simplifying assumptions that we make, and also under what conditions those simplifying assumptions hold. That's the message that I want to bring. Now, long story short, because I need to close, but if you want to visualize what the formula tells us is that if these links exist, SRT, ZRT, and HRT are not equal to 0. If there is a blocking object, SRT is not equal to 0 because of the structural scattering, ZRT is equal to 0, HRT is equal to 0. The structural scattering in the impedance model is embedded in another term, but it's there, okay? So what I'm trying to say is that if we try to compare multi-port network theory with communication theory, what we use in communication theory is a sort of mixture of the two models, okay, when we consider the direct link. But the important point is that communication theory allows us to model only this desired link from the RIS. Multi-port network theory allows us to model the desired link and the structural scattering or any possible unwanted irradiation that comes from the physical structure of the system. Okay, and this can be proved mathematically. So let's see whether all this mathematics is correct. So thanks to the help of Alberto, as I said, he's an expert in antenna and antennas and physics. So we managed to do some electromagnetic simulations in order to see whether what we were saying was at least correct in terms of trends. So the simulation scenario, these are simulations done in FECO, which is a full wave electromagnetic simulator, which is native based on the method of moments. Okay, so you have a transmitter that illuminates your RIS. Your RIS is modeled through a bunch of dipoles for simplicity, and then you want to steer your beam towards a receiver. Now, we studied different locations of the receiver here. For reason of representation, I show you this direction, but it works for different directions. So now, imagine that you sit on top of the RIS and you want to see how the RIS scatters the signal after you optimize it. Well, look only at the green line here. This is the transmitter that illuminates the RIS. How the RIS radiates. The RIS radiates. You can see there is a beam that points toward the transmitter. This is the actual structural scattering that communication theory is not able to model. And we have also the contribution that goes towards the receiver. So you can clearly see that there is this unwanted beam here. Okay. So what we did in the paper that I showed you before with Andrea and Alberto, we said, okay, could we try to optimize the RIS to reduce the impact of this structural scattering? Why this? Because basically we can try to play with the reflection coefficient here that we can optimize in order to create a beam that cancel out the beams that is contained here in SRT. The ones that I showed you before. So we brought an optimization algorithm where this is the desired term and this is the structural scattering. So what we want to do here is to maximize a weighted sum of these two terms, where omega is a penalty factor. So depending on how you set omega, you can give a priority to reducing the structural scattering with respect to the main beam that you want to create. So now let's look at what's going to happen here. This is the departing case where we actually need to consider the green line. So the green line is when omega is set equal to 0, which means that there is no we don't try to minimize the structural scattering. It's the conventional approach. And you can see your big beam here and also your beam here. Then if omega is equal to 1, so we introduce a penalty factor, we can see that we can reduce basically the beam towards the transmitter, which was the structural scattering, but we always have a beam towards the receiver. And this also if you change the omega. At this stage, given the problem formulation, we are not able to control these two beams independently because it's a weighted sum. So this was the first approach that we developed, but I think that here there is a lot to be done in order to try and to see how to control these two beams basically independently. That's a very important point in my opinion, and that there is a lot of stuff to be done in terms of optimization besides utilizing not dipoles but other things. I mean to obtain the results. So now. This was obtained in a diagonal configuration. Now, what is which is the challenge and what is the advantage of having beyond diagonal RIS when you consider this model? The results are taken from this paper, which I've already described to you. So beyond diagonal RIS provides quite a good contribution in these scenarios that I'm going to show you. First of all, I mean, by beyond diagonal, we mean the following in this paper. This is the conventional architecture where each antenna is driven by one impedance independently from the other. So the single connected architecture or conventional RIS. Then we consider another case, which is the group connected architecture, where we group some antennas and there is only interactions within the group, but there is a connection between, for example, here between two antennas. Okay, so you can we drive basically these two antennas together, and then there is the best that you can do, which is basically the fully connected architecture, which is the most complex to be realized, but the ones that you expect provide us the best performance. So there is always a trade-off, as we know in wireless. So now, what kind of gains this architecture can bring to us? Well, this is this is the departing point where we assume that the RIS elements are sufficiently spaced between them. Here we consider a spacing of lambda, just as a reference point. And also we have two kind of lines here. We have the case with mutual coupling. So basically we are considering the interactions between the antenna elements where they are very close to one another, and the case where there is no basically mutual coupling. Okay, that's essentially the idea. So now this is the case of where the interdistance is lambda. This is the case where the interdistance is lambda over 2, and we can start seeing a difference between when we consider the mutual coupling by design and when we ignore the mutual coupling by design. This is what happens when the spacing is lambda over 3, and this is the space when the spacing is lambda over 4. You can see that if you consider the beyond basically diagonal RIS, so if you consider the fully connected architecture or even the group connected architecture, the higher the mutual coupling, the more the gain that the beyond diagonal RIS can provide to you, and this gain is not negligible. Okay. So why basically this intuitively? So these are results obtained by utilizing the model that I told you, plus an optimization algorithm that was developed in this paper. Why? I mean, we expect this. Let me just show you this, and then I close. The reason why we expect this is because the more the mutual coupling, the more basically this matrix has off-diagonal elements that are non-zero. So it's pretty complex to control a non-diagonal matrix with a reflection coefficient which is diagonal, because you cannot control all the elements. So there the case where we understand that beyond diagonal RIS could provide a significant contribution. This is a clear example. And here we utilize the model that is free space, so it's electromagnetically consistent, and so everything, I mean, is compliant with the multi-port network theory. So in conclusion, what I try to highlight, I mean, in this presentation is that there is a need for electromagnetically consistent models for RIS, and that the beyond diagonal architecture may provide gains, especially if we have one of the case studies is in the presence of electromagnetic mutual coupling, which is something that we should in general consider when we study RIS or when we study holographic surfaces as well, or close to continuous antenna structures. So if you are interested in knowing more about these electromagnetic consistencies, this is one of the papers available in the special issue that I told you at the beginning, specifically dedicated to RIS, where there is also multi-port network theory. And this is a recent paper written with a colleague of mine, Marco Donald Migliore from the University of Cassino, who is an expert in electromagnetic theory and information theory, where we discuss this electromagnetic signal and information theory, included the role of multi-port network theory for modeling the mutual coupling, but not only that, also the degrees of freedom, etc. So you may want to have a look. That being said, I close here. The item that I didn't discuss is what happens when you use these devices at the transmitter, which now there is quite a bit of interest in that. This is maybe the newest architecture. You can apply similar techniques. So if you want to have more on the advantages of this architecture, I suggest you to read this paper, which is written with a bunch of colleagues, as you can see from the list of authors. And but I mean, the main advantage is trying to reduce the complexity, RF chains, increase the energy efficiency, and so on and so forth, with respect to conventional MIMO architectures that we have. That being said, I close here. I would like to thank again, I mean, Arman for chairing the session, and also for driving the ISG RIS, which was extremely important in order to promote, this technology, indeed. And Bruno and Matteo, for establishing this SIG, which I think is very timely. It's very interesting. And I look forward also to participate to the next webinars. With that, thank you very much, and I am very happy to take questions if you have.